back and look at segments in circles. So we're stopping right now talking about angles, because that's one thing that kids have trouble with is differentiating between angles and the segments in the angle. So we're kind of done with angles for now. We've done inscribed, we've done central, we've done angles in, on, and out of the circle. Now we're going to talk about segments in the circle. All right? So the first one, the first theorem or the first rule that you have to know is that when two segments are tangent to a circle from the same outside point, okay? So I take a point outside, anywhere on the circle, anywhere outside the circle, and draw a tangent line, two tangent lines to that circle. The distance from that point to the point of tangency on both of them is equal. Okay? So obviously that lends itself to solving equations. Right, 4a plus 2 equals 5a minus 32. Okay, so that's the first theorem that you have to know. That when you draw from the same point to the 2 points of tangency, so you kind of make like an ice cream cone. The two sides here, the lengths of the two sides are equal. So if I wanted to find out what a was, I would do 4a plus 2 equals 5a minus 32. I would subtract 4a and add 32. And that would give me a is equal to 34. Okay, and we're not talking degrees anymore, we're talking actual lengths. Okay? All right. And this is I don't think we're going to do this proof, but this goes back to the theorem that we learned from the computer activities, that if you draw a radius to a point of tangency, it's perpendicular to the tangent line. Okay, yeah. Yeah.
Oh my God.
Okay. All right. Let's see. All right, so let's take a second and do this one.
All right. So I made EF equal FG. So 2 and 3 plus 6x equals 14x minus 8. Sorry, it's horizontal or diagonal. And then I distributed to get 6 plus 12x equals 14x minus 8. That's the distribution thing right there. And then I added 8 to both sides. Then subtract the 12x from both sides. So 14 equals 2x, then divide both sides by 2, and x equals 7. So then I plugged it back into FG. So 14 times 7 minus 8, and 14 times 7 is 98. So 98 minus 8 equals 90.
Awesome. Great. Good job. All right, the second thing, if I can find it here, is, okay, perpendicular bisectors. in a circle, the perpendicular bisector of a chord is a radius. Okay, and that is actually what do you call it when it goes both ways? No, not contrapositive.
What do you mean?
Biconditional.
Oh my
right.
God, I was right.
It's biconditional. Right. So if the if it's a radius, that's perpendicular, it bisects them, and if it bisects them, it's a perpendicular radius. Works both ways. All right. So if I want to know the length of BD, how would I go about doing that, you think?
I have a question.
Yeah.
Is 2 and 3, like 5 is the whole radius?
Right.
Okay.
Right. Radius length is 5. So from BD to E is 2, and from C to A is 3. But what if I want to find BD? Actually, all I'd have to find is like CD or CB, right? Since it bisects it, and then multiply by 2. Exactly. It's our best friend, right? When all else fails, make a right triangle. Okay? And what do we call the distance from A to D? What is that? Well, it's a hypotenuse, but it's also in the circle, it's a radius. So Mary just told us the radius of this is 5, so this must be 5.
Wait, how is it? Can you say that again?
Because the distance from A to E, that's a radius, right?
Yeah.
So 3 plus 2 is 5. And then the distance from anywhere from the center to anywhere on the circle makes a radius, right? So they're all 5. Okay? But yeah, somebody already said it. What's the length of this side? It's a 3, 4, 5 triangle. It's a Pythagorean triple. So that's 4. What's that one? 4. So the length of BD is 8. Good. Good. All right. All right. Those look fun, don't they? Okay. So I don't have another one. Let's think one up. So I've got a circle. Okay. I'm gonna draw a chord. Okay. And does that look like the center from the distance? Pretty good. A little bit what?
It's good.
Down. Like that. Okay. Okay. So here's my radius. It's perpendicular, so it bisects the chord. Okay. And if this is 2.5 and this is 6, what's the length of the chord?
Okay, the first thing you do is you can add those. So I added 2.5 and 6 together, and that got me 8.5. And then since that's 8.5, if you kind of draw that, you know that this is 8.5. Wait, just kidding. And what I did was I did the a b or a squared plus b squared equals c squared. So this would be b, this is 6, and this is the 8.5. And then I did 6 squared plus b squared equals 8.5 squared. And that's 36 plus b squared equals, what did I put, 72.25. And then you do subtract 36 O2. Okay, and so then you know that both sides of those are 6.02. And when you add them, you get 12.04 for the chord.
Awesome. Good job. Okay. All right, and then the very last thing, we kind of already, we've been assuming it all along, I think, but I just want to make sure we all are on the same page, and that is when you draw a central angle, okay, if you bisect that central angle, it creates a two congruent arcs and two congruent chords. Okay, so if the angles are congruent, the chords are congruent, and the arcs are congruent. And then, just like angle addition postulate and segment addition postulate, we have arc addition postulate, and that is the measure of an arc formed by two adjacent arcs equals the sum of those two arcs. Okay, so if I take ED plus DB, what do I get? EB, right, right, good. Okay,